Hi everyone. Let's look at the idea of matrices and how this impacts us. If we look at the scheme, geometry dash, we will see there are items around here and we can cause it to move. And when we do that, that movement from one point to the other, I'm leaving the initial one as it is by the use of matrices. Even the idea of getting it to jump across will also be by the computer using matrices in order to move it from one point to another, just when we play with our controls. So the idea of matrices, which seems to be giving some of the students problems, we will start with remembering what the concept is and the order of matrices. So let's use a typical example. Let's look at Sarah here. Sarah wants 8 books for school. So we can put that information in a table, a tabular form. And of course, for books, we will have 8 of them. And if we write it in the matrix form, it will look like this. 2 square brackets with the number 8 in it. And this tells us that there is the information written across in one row. So we'll call that row 1. And if we think downwards, because we're trying to picture it like an array, then we have one column going straight downwards. So we'll say 8 would be in column 1. We can picture it writing like this, just as a square. And if we remember the words remote controls mean R for remote and C for control, just like rows and columns. So if we want to describe this information, which the computer would store for Sarah's books, it would have one row of information and one column of information. So it can be written as a 1 by 1. That's the description. Now, let's say Sarah wants for school, apart from 8 books, she also wants to have 6 different pens. So of course we could use a table and put it in. So we can put down a second column for pens, and of course the number 6 to go with it. And how does that change our matrix way of writing it? Well, if we look at the 8, we can slide that to the right and put in a 6. So our information is now 8, 6. There are no commas between them, no addition between them, just a space. And our information tells us that we have one row of information, but 2 columns. So in row 1, column 1, it tells us that there's 8, which means for us in this case, 8 books Sarah needs. And in row 1, column 2, the 6 indicates she needs 6 pens. And of course, we are doing it like a diagram. Then it would look like one square followed by another to the right of it. So we're actually forming some sort of rectangle. So the rows by columns would not be 1 by 1 anymore. It'll be one row by 2 columns. And if we continue now and say Sarah now needs 2 stickers as well, then 8 books, 6 pens, and 2 stickers. So she might have some Lubaloo stickers that she requires. Then we could put that in the table. And that is our simple way of representing the information. But now matrices is just a way of doing it faster. So how would the matrix look? We will have to move that back and put in the 2. So we'll have 8, 6, and 2. The dotted lines is just to show us the guide of where they're being placed. The 2 is in row 1, column 3. And of course, if we were trying to set it up like little squares, then we'd add a third square there. So we actually have a rectangle, 1 by, not 2 anymore, but 1 by 3. So there are different ways of setting it up. And this is our matrix form. So we have our tabular form that we're accustomed to, and we have our matrix form. Let's now introduce another one of Sarah's friends, Liam. Liam, he requires 5 books, 6 pens as well, but no stickers. So we can put that on the table as we're accustomed. So under books, we'll have 5, under pens, we'll have 6, and no stickers means we have 0 for there. So what happens if we want to represent that as a matrix? Well, it's quite similar to the table form. We'll have the 5, 6, and 0 as well. But of course, our square brackets needs to enclose those 6 pieces of information. So we can stretch it out, and we'll now have 5, 6, and 0 in a second row, or what we consider to be row 2. So that means we have 6 squares, which we can align. Instead of being a 1 by 3, we can have 2 rows by 3 columns, so a 2 by 3. So we're just trying to get different ways of representing it, because some of our students complain that they're having much problems, many problems with regards to this. So this idea of 1 by 1, 1 by 2, now a 2 by 3, that is considered to be the order of the matrix. So what happens now if we have a third friend? We have our little ninja, and he requires 3 books, 4 pens, and 1 sticker. So can we fit him on the table as well? Right. So we'll put in the ninja, and he will have 3, 4, and 1 to represent them, the information as required. Can we fit it into the matrix? And yes, we can. And we see our matrix is growing and growing and holding more and more information. Is it quite correct? Not yet, because the square brackets are not big enough. So let's make them a little longer. And what happens? We have 1 row representing Sarah's information, 1 representing Liam, and now 1 representing Mr. Ninja. So that's row 3. So we can actually identify even specific elements, because we now have 9 elements, that row 3, column 2 tells us that there are 4 pens that Mr. Ninja wants. So if we represented that in terms of the squares, then we'll have to add 3, 4, and 1, 3 more squares at the base. So what does that mean? Is our order still 2 by 3? No, not quite. It's now 3 rows by 3 columns, rows before columns. Even if we decided to ignore all of the stickers, then we'll have 3 bits of information from the 3 students, but instead of 2 materials that they require, books, pens, and stickers, we just remove the stickers. So it'll be 3 by 2 as the order. So let's recall that this channel here is made specifically for students who are struggling in mathematics in specific areas. And what has been highlighted in our channel, CSEC Math, is the area of matrices. And we'll be looking at the notes, specifically the introduction of matrices in this video. We have outlined how you can go through the entire CSEC Math syllabus on this channel by looking in the description down below. We also have a channel similarly for additional mathematics, which started from the beginning of CSEC Additional Math in 2012, with all the past papers up to present, and one for primary math. All those links are in the description below. So we just looked at the ideas of what happens. So now let's look at the definition and types of matrices. So remember, we just had this diagram indicating our matrix form, showing Sarah's information, Liam, and Mr. Ninja. So let's now take that and remind ourselves now, what did we get? Well, matrices could be represented as one square, or two going across, or three going across, or two layers, or three layers, or even making it slimmer, two columns or one column, and even more. So it is really as like a set of post boxes because it's this rectangular arrangement. Just like what post boxes will look like for an apartment building. Or if we think of Excel and the spreadsheet, it looks like putting the information like that, rows and columns in a huge array. So it is a rectangular arrangement. And of course, what fills it? In the first one, we can see 8, and then 8 and 2x, maybe 8 and 2x and 0.4. By the fourth one, and a tick, and a 0 and a -1. By the 3 by 3 below, we can actually have x plus 1 included, 1/3 as well. So what does this tell us? That matrices are rectangular arrangements of what? Of numbers, of symbols, of expressions like 2x, like x plus 1, like ticks, which helps to give us information readily accessible. So let's consider what is a null matrix, because we are now going to look at different types of matrices. So a null matrix would mean, if we clear that information out a little bit, a null matrix would mean that each one of the elements or items of information is 0. So all the elements are 0. If we consider a null matrix and now look at what is a row matrix. A row matrix will be actually looking like something which is horizontal, going from right to left. So if we look at these different shapes, which one goes from right to left? Well, the first one up on top, that looks like it's going from right to left. The second one, it looks like it's also going from right to left. What about the third one right below it? Yes, it's also going from right to left. What about the fourth one? Well, it's not actually one row only, but it's more than one row. So what can we tell about this? Let's put in the order so we can see. The first one up on top was a 1 by 1, one row by one column. The second one had how many rows? One row by two columns. The third one has one row by three columns. So hopefully we could see a pattern that all of these are row matrices. What about the fourth one? Is that one row by something? No, it's two rows. So that doesn't count. So if we were to explain what is a row matrix is one which only has one row. So it's one by some other number. It could have so much information, it could be 1 by 28 for all 28 students in your class. This is their math mark. So one long row across. Now, just as we have row matrices, what about column matrices? So a column matrix will be moving vertically, if we consider it as just being one post up and down. So if we look at those arrangements before, which one looks like it only has, can qualify as a column matrix? The first one, the information is going up and down. What about the second? No, it's two columns. The third, three columns. Is there any other column matrix? Well, there's one more. It's down here, where it's one column with 3 bits of information. And that is a 3 by 1. So the 2-column matrices represented here are the 1 by 1 and the 3 by 1. So what we can say that a column matrix has only one column. It doesn't matter how many rows. So it could be 15 for all 15 students in class who like to play cricket. So it'll be 15 by 1. This is the list of topics that is being considered for our CSEC assessment. What are we looking at? Number 9, vectors and matrices. And in vectors and matrices, now with the new syllabus, there are now 3 modules in which the syllabus has been revamped, and you can write it as all 3 modules together, or each module individually, or a pair at a time. And if that's so, and we're looking at the particular topic of matrices, it only appears in module 2, not module 1, where we have 4 multiple choice questions and 4 marks in the long paper. And it appears in module 3. So there's a first part of vectors and matrices, it's in module 2, and there's a second part of vectors and matrices, which is in module 3. The first number on the left in each one is the number of multiple choice questions where it has been assessed. So there's 4 multiple choice questions in module 2 and 3 in module 3. And in the longer paper, paper 2, there is 4 marks in module 2 and 9 marks in module 3. And it may even be assessed in the maker paper because SPAs have been removed presently. The 032 paper, that in that maker paper, that there are possibilities and matrices may also be addressed there as well, but it will be within the same content that we're covering. Let's now look at other types of matrices, such as square matrices, diagonal matrices, and the identity matrix. So we know that matrices are a rectangular arrangement. So if we look at the sum of the different types of matrices here, can we see any which are square matrices? Well, the first one. Any more? The third one, which is a 2 by 2. And of course, the 3 by 3. So let's think of the orders here. The first matrix is a 1 by 1, 1 row by 1 column. The second matrix is a 2 by 2, 2 rows by 2 columns. And the next matrix is a 3 by 3, 3 rows and 3 columns. So what can we say about a square matrix? It has the same number of rows and the same number of columns. So even if it's 10 rows and it's a square matrix, it means it has 10 columns. And for vast pieces of information, like playing video games, there may be 50 rows by 50 columns of information for each motion. So now that we got what a square matrix is, now let's look at what a diagonal matrix is. A diagonal matrix has certain qualities, one of which, in order to be a diagonal matrix, it must first be a square matrix. And when it's a square matrix, it builds on the idea of what a null matrix is. And let's recall, if it's a null matrix, all of the elements are 0. But building on that idea of a null matrix, the diagonal matrix is slightly different because it takes into consideration the main diagonal. So we have 3 square matrices here looking like null. Let's look at the main diagonal. Let's start with the 3 by 3 below. Might be the easiest to see. And I'll put a dotted line through the main diagonal from the top left to the bottom right. If it's not a square matrix, we won't be able to get a main diagonal like that. Now that we have that, what it is, all the elements on the main diagonal, right, those have non-zero elements. So in this case, 8, 4, 1/3. One element or two elements could have been 0, but on the main diagonal, at least one of them must be not 0 or non-zero element. Let's look at the 2 by 2 main diagonal, top left and bottom right. And as long as it changes to something else, 8 and 4, then that is also a diagonal matrix. And the 1 by 1, the main diagonal goes through the one element, and that has to be non-zero. So in this case, it's 8. So we have a square matrix in terms of its shape. We have a diagonal matrix, which sort of looks like a null matrix, except for the main diagonal. And finally, we have an identity matrix. In an identity matrix, it is a diagonal matrix. That means it's a square matrix. Most of its elements are 0, except on the main diagonal. And in an identity matrix, what happens is the main diagonal, all the elements on that is 1. So let's look at 3 by 3 and we could change them. So it's a 1 by 1. And then on 2 by 2, there's 2 ones on the main diagonal. And in 1 by 1, there's only one element, so there's 1 there. So this gives us different types of matrices we've covered. Let's now go look at the operations, addition of matrices. Can we add two different pieces of information? Let's recall we have this idea of how the matrix looks. And let's go look at Sarah again. In this case, Sarah has 7 books and 6 pens. 1, 2, 3, 4, 5, 6, 7 books and 1, 2, 3, 4, 5, 6, 6 pens. And her friend Liam has 5 books he brought to school that day. 1, 2, 3, 4, 5, and 1, 2, 2 pens. So, knowing this, we can write that piece of information there. Remember we have columns and we have rows. So this is a 2 by 1 right now. Let's look at it like that. 2 rows by 1 column. And that is a 2 by 1, which is Sarah's information is coming in first. And her information is she has 7 books and 6 pens. And then, so we're writing it in matrix form. And of course, Liam has 5 books. So we'll write that on top. We're putting them in blue, trying to keep it color-coded so you could follow it well. And 2 pens. So if you notice, we have a 2 by 1 matrix, 2 rows and 1 column. And we're able to add it to exactly a 2 by 1 again. The orders must agree. Otherwise, we won't be able to add. And that gives us a 2 by 1, which is, if we put in there 7 and 5, that gives us 12 books. And if we bring the pens, 6 pens and 2 pens, so 6 and 2 is 8. So we have 12 books and 8 pens. What about if we have 2 Lubaloo stickers that Sarah brought to class? Then can we put that information? We need a third row. And of course, that means we need to have 3, our answer will be 3 pieces of information accordingly. So let's change Sarah's information. 7 books, 6 pens, and 2 stickers. And we want to add. And if we're adding this, remember that's a 3 by 1, and we're adding to a 2 by 1. Will it give us that? Well, we have a problem because right now, how many stickers does Liam have? We don't know. So could we add these two pieces of information together? We can't because we don't know how many stickers he has. We don't know if it's 0, if it's 12, it's 4. So what do we have right now is a 3 by 1 matrix from Sarah with her information and a 2 by 1 matrix from Liam's information. And if we try to add that, we are not able to get a 3 by 1. We're not able to get 3 pieces of information. So what this tells us is that when we're adding matrices or subtracting, then two matrices to be added or subtracted must have the same order. So if we now have this piece of information that Liam has no stickers, then we can replace the question mark by a 0. And now it's 762 from Sarah, 520, which means Liam's information is a 3 by 1. So we have a 3 by 1 from Sarah in terms of the matrix formed and another 3 by 1. And if we add 2 of those, we're going to get a 3 by 1 where we have information from the pens, a total of 12, of the books, a total of 12, information from the pens, which is 6 and 2, 8, and then 2 Lubaloo stickers, and none from Liam. So now we're able to solve. So it's very important to understand that when we're doing this, in order to add or subtract matrices, they must be of the same order. Now, if we consider it as 3 containers and do it a little differently, instead of writing it as column vectors, we can write it across as row vectors. So let's put information for Sarah, and she has 7 books, 6 pens, and 2 stickers. And you will find many times it's written like this as row vectors rather than column. Either way, it's easy. You all can handle this. Liam has how many books? 5 books, 2 pens, and how many stickers? 0 stickers. And we have to add this. Some students get a little confused, and that's okay. We can think about it a little differently. We can take this whole thing and carry it down below. And it's like normal addition. How many books do we have in all? Let's see. We have 7 books from Sarah and 5 from Liam. So 7 and 5 is 12 books. We have 6 pens from Sarah and 2 pens from Liam. So it's 8 books. And we have 2 Lubaloo stickers from Sarah and none from Liam. So that gives us 2. So we still get the same information, 12, 8, and 2, whether we did it as addition or subtraction of row vectors or column vectors. The key thing is that the order must be the same. On this left-hand side that we just did, it was a 1 row by 3 columns, or 1 by 3. Added to a 1 by 3 gives us a 1 by 3 answer. The identity for matrix addition, since we're trying to be a little comprehensive in the notes here, and students, when they grasp this, it's easy to build on, and the rest of matrices becomes very simple. So when we think about addition or subtraction, then we can think of the idea that it's real numbers. So let's think of Liam. Liam has 5 books. 5 books, and how many more books will give us 5? And why we're doing that, it's because this is what we've been doing all the time. 5 and what number will give us 5. That is called the identity, as long as we can figure out what that is. So if we want to find the identity alone, we can minus 5 from both sides from your typical algebraic solution. So 5 minus 5 is 0. It disappears on the left side. So what that means is we're left with I is equal to 5 minus 5. The identity addition, and the identity works out to be 0 when we're using real numbers. So the identity for addition or subtraction is 0. Now what happens when we're looking at matrices, the plural of matrix? We have 5 books and 2 pens from Liam. And how many more books and more pens do we need so that we end up with the same amount? The same 5 books and 2 pens. So this says we think about Liam, and the identity matrix will give us back Liam. So if we subtract Liam from both sides, we'll get that the left side will disappear. We'll have the identity is Liam minus Liam. And let's show it. Let's put in the matrices there so you can see it's a 5, 2 matrix for Liam minus itself minus 5, 2. And it's not just 0. It's 0 books and it's also 0 pens. So what it tells us is that when we talk about the identity for real numbers, it's just 0 when we're adding or multiplying. But when we're talking about identity matrix, when we're doing that, the identity is the same order as the matrix we're using. So we're using 2 by 1, 2 rows by 1 column. So the identity for that is 2 rows by 1 column, all zeros. So the identity for addition or subtraction of matrices is the null matrix for that type. And let's see how this is useful in our games. If you're playing Super Mario Brothers, let's say, then he may be on the left side, and when you toggle on the switch, we click right, one press on it, it means what it's telling the computer is take this image and add 5, 0. That's what one of those may indicate. We're using an example, which means move 5 places to the right and 0 places up. So that will just mean that we run across. And if we want to move to the right again, we press the correct keyboard if that's what you're using, or joystick, and it will give that indication again, another 5 to the right, and you're not jumping up or down. And we want to go again, and next time we may get 5 to the right, and we're still on the horizontal ground. And if we press again to the right, at this point, it will be 0 at 0. And what does that mean? It means that we're not moving to the right or left, we're not moving up or down. So what we have is the identity matrix. So for certain situations, when we press to the right or move to the right on the joystick, it means we're moving 5, 0. But when we have come into obstructions and we do the same thing, it's actually giving us the identity matrix. And the computer is registering that. And you will see that's why Mario doesn't move. Scalar multiplication, which is the last major thing we're doing here. So let's consider the idea of Mr. Ninja. He has 3 books, 4 pens, and 1 sticker. 1 pink Lubaloo sticker. That's his favorite color. So N for ninja, we can represent this information as 3. Trying to use the same colors, 4 for pens, 1 for sticker. And what happens if we have another ninja here? but we're actually considering that he's doing this 3 times. So there are 3 sets of Ninja information, which means there are 3 more books and 4 more pens and 1 sticker, and another 3 and 4 and 1. So how many books do we have in all? It's an easy count. 3 threes are, and we can see it's simple standard multiplication. 3 times 3 for the number of books, and then 3 sets of 4 pens and 3 sets of 1 sticker. So that is total of 9 books, 12 pens, and of course 3 stickers. So if we're doing, this is, the proper name is scalar multiplication. What it's actually doing is just taking the whatever factor we're multiplying by and just doing direct multiplication to each one of the items. So it's considered if we have some matrix A, B, C, or A, B, C, D, E, or so forth, and we're multiplying by a constant, K is represented as a constant, K times A, then it's K times A, B, C. So it will be KA, 3 by 3, KB, 3 by 4, KC, 3 by 1. And in terms of how does this play out, if we consider, we have the idea of Pac-Man, and he's eating and getting larger. Then we can use K as 4, and that means he gets 4 times larger. And after a certain period, the K is 1/4. So he reverts to 1/4 of its original size. Equality of sets. So let's consider we have a sports store, and with this we have 2 branches, and we wanted to have the same amount of stock in each of the branches. So the first store had shoes, these 4 items we're looking at, t-shirts, female shoes, and of course female long sleeve t-shirts as well. Male and female shoes, male and female t-shirts, 4 items. In the first branch, 24 shoes were revealed, male ones, and they stocked 15 t-shirts, 19 pink shoes, and of course 32 blue female t-shirts. And in the second, so let's put that and make it look like it's a matrix. All we need to do is put square brackets around it. 24, 15, 19, 32. So we could see it's a 2 rows by 2 columns, a 2 by 2 matrix. In the second branch, the same things were sent, except some of the packages ended up opened. So what we had a large box with the blue shoes, a set of them, and pink and so forth, so different containers for each one. And by the time we went to the second branch, 2 of those containers showing the blue shoes were there. And that has the same amount as in the first branch. But when they sent the male tops, there was a box with it and 2 extra ones on the side. And when they sent the pink shoes and they opened it, there was 1 less shoe inside of this box. And finally, there was 1 box with the tops. Now understand that if the 2 branches have the same exact stock, the same amount of items in each of the branches, then let's consider it to be like a scale and that we're equal. That we have 24 blue shoes, 15, 19, and 32. And on the right side, what do we have? We have two, let's say 2p to represent those sets of blue shoes. We have one box for the male tops. So we could Q, we don't know how many in there, and two more. That's what's sent. And when we look at the pink shoes, there's one box of pink shoes. Let's call that R minus 1. And finally, let's call that S. Now, since it's the exact amount of stock in each branch, therefore that says something. It says, let's put little square brackets around them to consider that they are equal. So these are equality of sets of matrices. So if the blue shoes are equal, it tells us that 24 is the same as 2p. So that means each of those blue boxes would consider to have 12. Now, how many were in the yellow or orange top on the right side in that box? Because we know 15 went in the first branch and the box plus two loose ones came there. So we could realize that when they packaged these tops, it had 13 in a box and they had to send two extra. And when we compare the pink shoes, there were 19 in the first branch, and in the second branch was a box of pink shoes missing one. So R minus 1. As such, we can figure out that a full box of pink shoes is really 20. 20 minus 1 is 19. And finally, if we compare the blue tops, then a box of blue tops is 32. Hopefully, you can see that what we're saying here is that matrices are considered to be equal when every single item matches the other item in the two sets. So the first row, first column item in the first matrix is equal to the first row, first column item in the second matrix. 24 is equal to 2p. So that's what we consider to be the same. And of course, for them to be equal, they must have the same order. If they don't have the same order, they won't be able to line up. So equality of these matrices means it's a perfect match of all its elements. This now brings us to the end of this video on matrices, the first part, where we looked at what is a matrix, the order of matrix, the types of matrix such as square and null, and the operations of addition, subtraction, and scalar multiplication. So don't forget to add any comments down below and like the video accordingly. Our next video in this series, which is part 2, we will be looking at matrix multiplication. And don't forget to look at the description down below where you'll be able to see the entire route of the syllabus or within this series as well, which ends with 3 sets of videos on past paper questions based on this.